All right, we're live.
Hello, and welcome back to day 10 of India Science Month Online. I am Misha, a program associate at India Science Festival, and on behalf of the entire team of ISF, I welcome you back to hear with us the voice of science and celebrate technology. India Science Fest and India Science Month Online is a one-stop destination for all things themed around space, robotics, healthcare, and science communication. We are joined by researchers, scientists, educators, teachers, students, artists, and science communicators in this month long celebration. Our panels have been exceedingly engaging so far, and we've had speakers and panel discussions ranging on a wide variety of topics. Some of our sessions have had post session closed door interactions with our scientists, and if you're interested in participating in those, do join us. Don't fret if you have missed some of our sessions, for recordings of all of these are available for watching at our YouTube channel. We've also had interactive workshops with a wide variety of experts, ranging from storytelling and science-based art to exhibitions by the Science Gallery Bangalore that are going to continue till the end of this month. We have games, quizzes, treasure hunts, Pictionaries, and jams that are still live on our platform, and you can participate in. Perhaps one of our more unique offerings is the postcard program. We ask you to send us postcards to our headquarters in New Delhi, and then we will fly them into space for you in tie ups with Blue Origins. And when they come back, stamp them and send them back to you for a unique once in a lifetime keepsake. We've had a fascinating lineup so far, and we have a fascinating lineup today also. I would also like to point out that our events are free to attend for all. Do invite your friends and family to join us not only for the webinar, but also on YouTube Live, where we stream our sessions. Before we begin, we'd like to conduct a quick poll so that we can understand the demographics of, of our audience. There should be a poll on your screen right now, and I request you to please answer those questions. We have a fascinating mixture of people with us today. A large part of our audience comprises of college students and younger school students, as well as a few professionals from tech, life sciences, and medicines, as well as some faculty members. There is going to be another poll on your screen. There's going to be another poll on your screen in just a second. And I request you to please answer questions for us there also. Great. It appears that most of our audience know little about the topic but are very interested in learning more about it. We also run a very exciting Twitter contest where we ask you to share your thoughts about the live sessions, tag us on Twitter as Science Fest, and we will ensure that the best tweets not only gain attention but also win exciting prizes. Let's begin. For today, it gives me great pleasure to have with us Professor Lavanya Marla from the University of Illinois at Urbana-Champaign. She's going to talk to us about how mathematical models can help bring healthcare to all. Professor, can you switch on your video, please? On
Uh,
behalf of the team of India Science Fest, I am very grateful that you could take time out from your schedule to speak to us.
Misha, could you enable video?
Yes, just you should be able to switch on video right now.
It says I cannot start because the host has stopped it.
Mm-hmm. Shruti, can you please enable video sharing for.
Yeah, just give me 1 second.
Professor Marla is a professor at the Industrial and Enterprise Systems Engineering Department at the University of Illinois and Urbana-Champaign. And her talk today focuses on how we can use mathematical models to ensure that ambulances can reach people on time. It's a talk that we are very excited about, and certainly something that seems very pertinent in today's times. Over to you, Professor.
Yeah, thank you, Misha. Thank you, Shruti. Uh, wish to thank India Science Fest for inviting me. It's a great pleasure to be here. I've been hearing about the events from last year and how exciting and engaging it was for the audience. And I want to share some of my work with you and the different kinds of India specific work that we are doing, as I believe that will be the most interesting aspect to the audience. Um, let me share my screen. Okay. Uh, I hope you can see the PowerPoint slides here. Uh,
Yes, you're good,
so,
Professor.
great, great, thank you. Okay, so this talk is focused on one aspect of my work, which is about healthcare delivery, and in particular, the idea of getting ambulances to people. In general, my work focuses on complex systems design with connected physical infrastructure. It could be anywhere from logistic systems, airline systems and airport systems, and emergency medical services and other healthcare delivery services. And I bring a host of tools to these, ranging from data mining, prediction, optimization, simulation, with the goal of planning for these systems. How do we design them before they're put into operation? And how do we look forward as we design these systems? And as we get near real-time information, how do we reconfigure them so that they can serve the needs of the various stakeholders of the system, considering the different kinds of potentially conflicting stakeholders' ideas and their different needs? We also focus on as these systems are being put into operation, and often the world is uncertain, and as these uncertainty manifests, how do we repair and recover these systems so that they perform and function robustly to serve the needs of everybody involved? So I'll focus today on the emergency service aspect of my work, and I'll bring particularly the focus about emerging settings, including those in India. This is one snapshot of a city in India. And you can see that near the center of the city, you have this quite dense cluster. What you have as in the picture are calls, which we have a balloon here, and we have a wheelchair symbol in it. And wherever we have another balloon with a plus symbol in it was where the ambulances were located across the day during the functioning of this particular emergency service in a city. This was a while ago, but this serves to indicate how much the demand is increasing for these kind of services across different cities in India. About 10 years ago, only about 10 states, and that too major cities in each of these states, were having these centralized emergency service systems. More and more, like most of the people in the audience would already know, systems like 108 are coming in many, many more cities. And what we want to look at is how are these systems designed? What is behind the engineering of these different systems when we want to serve the population? How do you think about it? in the context of the entire city, the entire service region of interest. So here again, just to emphasize, you have the plus sign indicating the bases. That is where the ambulances are located. And these bases were in some sense prefixed by the operator. And then we have all the calls arriving. And of course, we don't know where the calls are going to arrive. This is a stochastic process. And basically, there's a lot of uncertainty in where calls might arrive. So you have this entire system. For now, ignore the white and red and greens for the callers. I will tell you later what they mean. So this problem is when we play this out over time, calls keep appearing at various places, and you have ambulances that may be busy or free at the time. And so you have to make decisions. As the operator of the system, multiple decisions have to be made. So let me focus on what happens to this notion of ambulance provision, or formally what is known as emergency medical services, in the context of emerging economies. So first of all, these systems are highly resource constrained in these emerging settings, because as the fleet size and other provisions are being made, you can have very few ambulances per capita. And prior to these 108 type centralized providers that are being put into place, previously there were no centralized providers. So what used to happen was there were these ad hoc taxis or hospital ambulances that were used to provide these services. So you call maybe a particular hospital and say, can you send me your ambulance? Or somebody would just take a taxi to get to the hospital. And part of this was due to the lack of awareness of what is called en route stabilization of the patient. So the idea was simply, can we get to the hospital, rather than as we get there and before you even start to think about where the provision of health begins, that is, as soon as somebody reaches the patient, tries to do some stabilization on scene where the patient is first, and then take them to the hospital, and en route as well, do any kind of other stabilization needs that are required before the patient can be admitted to a hospital. So some lack of awareness was present in the system, and therefore there was this not a differentiation between an ambulance and maybe a taxi, which is simply a means of transportation. And when we think about systems like India, Africa, and many other cities, we're thinking about very large scale cities. What I mean by that is very densely populated areas. And also these are served primarily as a public-private partnership. Primarily these are state funded, and therefore the state's objectives in serving the entire population take precedence over a private partners or the operator's preferences here. And so the operator is working on an, they design and operate the system, but they are responsible and accountable to the state in what kind of metrics are actually they optimize for and how they serve the system. And it takes a lot of time, almost the first 5 to 10 years for users. That means the average person to adapt to the system and understand what's happening. And so you have this interesting framework of this 108 centralized system that's layering on top of these existing hospital ambulances or taxis or other existing frameworks in the system. And I'll focus on these different aspects of these. In fact, I'll bring about what are the unique aspects that are different from, let's say, other mature emergency medical service systems across the world. And I'll bring about different, this sequence. I'll talk about the data a little bit, how data was used, what kind of mathematical models were used, and what kind of decisions we aim to make using those mathematical models, and finally, what the impact was of such mathematical models. So we have these goals, which are strategic as well as tactical. And the strategic goals are that of saying, what is the size of fleet that I need to have? And what are the locations of the ambulance bases that I need to have? Some of these are dictated from practical considerations, others using the mathematical considerations. From a tactical point of view, I have some other objectives. where do I locate that fleet? Let's say I have base locations and I have a fleet, but how many ambulances in each base? And during the day, do I need to move the ambulance around so that if there are peaks and valleys occurring, how can I actually address such peaks and valleys as they occur? And next, another question of what to dispatch. That means if a call arrives at a particular location, then which is the ambulance? Where is that located and who needs to go serve that particular patient? So for example, this is the problem of saying, take that fleet and locate it across the entire city. And once you have that, demand keeps occurring across the city, of course, in an unpredictable stochastic manner. And how do you actually use that information to actually locate these ambulances? And then as that demand may change during the day, maybe I have to relocate or redeploy some of those ambulances through the day to really answer the needs of the population. Despite the resource challenges, what are the big advantages in these particular cases? One is that you have a tremendous data collection system that is set up in place because of the IT infrastructure and all the cell phone traces, GPS traces, and other things that these ambulances are equipped with. We actually have information about different things, how movements were happening based on historical data, where demand was occurring and how did that change, whether seasonally, on a daily basis, or on a weekly basis, and so on. And so we want to estimate different things from that particular data. We want to estimate things like arrival rates and call patterns and travel times and so on. And we want to use that to be able to serve this system better. Sorry, 1 second. I guess I have to share the screen again here. Okay. Okay, so let me talk about some challenges which are unique to these emerging settings. There are these high resource constraints and a lot of traffic congestion in the system. That means as the ambulances are moving, they may encounter, because of limited road infrastructure, they may encounter slow movement times, either due to traffic or due to the road conditions. Then these influence significantly what response looks like. And response is one of the most important things that we care about in terms of how quickly can an ambulance get from where it's located to the patient. That means that from the patient's point of view, what we care about is when did they call and when did they actually have an ambulance arrive to where they are. So that's one of the novelties of the system. The second is a notion of human behavior, which I will explain shortly. The other is this idea of the decentralization of ambulance services. And then I'll talk a little bit about looking to the future, how medical drones, both in emerging settings and in mature settings, are being used to actually serve people and improve service levels across cities and across regions, which may be served at very different levels. So let's look at the first novelty aspect. And in this case, given these different challenges of high congestion and low resource constraints, the question is, how do you best locate ambulances, right? The first is we use a multi-level approach. At the first approach, we are learning from the data, what the demand rates look like in different regions of the city, how to actually even separate the city into regions, and then estimate from historical data and evolving data what demand looks like over different periods of time. Is it a similar pattern even though there's stochasticity, or does that pattern change and have peaks and valleys across the day or across days of the week and so on? We also learn traffic patterns. That means between the same 2 points, when we want to send an ambulance, which is the fastest ambulance might change over a day. That means if there is a bridge between base 1 and let's say a particular neighborhood, and there is just the regular streets between base 2 and a neighborhood, in the morning times, it might be easier to cross the bridge and get from base 1 and serve people in that neighborhood. But as traffic increases, it may be possible that during the day, crossing the bridge becomes much harder. Therefore, the nearest ambulance is actually from base 2 or a different base, but not from base 1. And we want to capture those evolving characteristics. So we use data mining and learning for that purpose. We also want our system to adapt to different modes of transport. In different cases, for example, in places like Assam, there are water ambulances. So we want to capture how speeds vary when you have the road ambulances versus, let's say, the water ambulances. And that can be captured in the kind of models that we have. And then we want public acceptance. Maybe ambulances are slow because people do not realize that they have to give way to ambulances in a more instinctive fashion. And that, because the system is still adapting, that takes time. So we capture all of these in what we call as system or city characteristics. And then we plug these all into a model which makes decisions. And that is based on a combination of simulation and optimization. And the statistical, we want the simulation model to be statistically significant. And that could be based on simply a kind of model that I'll show, or a queuing model, or many different sophisticated mathematical aspects that could fit in there. And then the optimization algorithm is a decision-making framework that says, I embed the simulator into the optimizer and understand something about the objective to get near optimal decisions. And in this case, we are making those decisions about where to locate ambulances and where to redeploy them as the day progresses, as we see what is happening through the day. And if we forecast what's happening, how can I move ambulances around so that they best serve the demand of the city? And here I want to give a shout out to my co-authors on these different papers, and those who are interested in looking at some of the math can reference these papers that are here, and they're available on my webpage as well. Okay, so let me tell you why this problem is hard. Why do we care and why it is hard, right? If it were very easy and if I could just locate things across the city, it should be fairly straightforward, right? So let's think about this system. Let's say I located 4 ambulances across the city using this in this simple example. And they're located here before, let's say, the demand starts evolving through the day. Let's say I get my first customer, I send the nearest ambulance to that customer. And then another customer comes, they could have been served better if this first ambulance had been available. But then I send the nearest one available at that time, which would be that. And so they let's say served in 30 minutes. And another one arrives. And that could be, that demand point could be here. And that I send the nearest ambulance. And when this particular demand arrives, it could be that the nearest ambulance at that time could be much farther away, and maybe that caller has to be turned away. What happens is, because of what happened in the past and how demand evolved over time, we get what is called dependencies in these systems. So all these decisions about where to locate one ambulance here and one ambulance there and other things are interlinked. And why are they interlinked? If I had a lot of resources, if I had many ambulances, we would not have these interlinkings. But the fewer resources I have, the tighter systems are coupled. And therefore, we have dependencies arising in the system as demand evolves. And of course, demand is unpredictable. So if I knew it, of course, I would have placed things better. So if I knew more about the system or about demand patterns in the system, perhaps I would have done this. That means move that ambulance from there to this point. And that means I could maybe have served these callers in this pattern. Of course, this is if I knew what was happening, right? If I knew how demand was going to evolve. But what I can do is, with my predictions of demand, understand not only one sequence of how demand evolves, but many, sample many tens of thousands or millions of such sequences of how demand might evolve so that my decisions can be statistically significant. So if I change the allocation of ambulances in the system, the dependencies change. In fact, the dependencies are fewer in this system. So if I can have a way to arrange my resources in the system such that the dependencies are fewer, then I have better service levels for all the population. That's the key idea. Can I represent what's happening in the system, maybe as a graph using a simulation framework, have costs on the allocations, which would be the arcs represented by these graphs. And as I break more and more dependencies, I add ambulances or reallocate ambulances across the system, I have fewer dependencies, which means better and better service levels. Okay. So what we do is embed this within a greedy simulation optimization algorithm by actually considering the nature of the objective function that is described by these graphs. We exploit a property called approximate submodularity. And I will not get into the proof of that, but the idea is, can you understand the technique of what is happening precisely and the underlying mathematics so that I can make a better decision. Suppose I want to allocate n ambulances among m bases. This greedy algorithm adopts a strategy and says, suppose I have 0 ambulances in the system currently, test adding this ambulance at each location and simulate this over millions of different paths of calls. That means these are different probability paths. These are coming from the data mining and analysis that we did previously. And we said these are the patterns that are evolving. So those patterns are embedded within the simulator, and we say, where is the best way I can allocate the first ambulance? And locate that ambulance there, fix that there, and repeat. And this is a specific algorithm called a greedy algorithm. And it turns out under certain structures, this can do very, very well. And so essentially, what we are doing is leveraging that mathematical property to do what's called a very highly tractable, that means a system solution algorithm that runs very fast, but also gives us very good decisions. We also show in the papers that these decisions are close to optimal in the setting that we are looking at. And we can solve them very fast, which means I can use it for when I plan in the beginning of the day where to locate things, or during the day as ambulances become free. Some ambulances which are idle can be repositioned across the network, and I can do better service by moving them across the network. So what we find is based on different objective functions, we care about how many people are served within these thresholds, so 15 minutes, 30 minutes, and 60 minutes, and so on. We find improvements in all these metrics. And fundamentally, what is the one metric that's the most impacted? The number of cases in which earlier people were told that the ambulances are busy and we cannot serve you. And that dropped from what it was to 40% of its original number. Right? So we were able to show that many more people were served. People who were earlier rejected service were now allowed to serve. And beyond that, we can show that instead of simply locating ambulances in a plan and then leaving them as they are, after they serve, they come back to the original location. If I'm able to move them across the network, predicting what happens in the next half an hour, 1 hour, or these different intervals of interest, we can do even better. And again, the most impacted metric is how many people you can reach using these. The number of callers you can serve as you are able to redeploy and place ambulances in a better way. We also, of course, find improvement in the number of people served within the thresholds of 50 minutes, 30 minutes, and so on. But this is the one that's the most impacted. That means people who would have been turned away are now being able to be served. So that was the first story. That means better math, understanding the underlying math, can help you do even better with respect to these different services. Next, I want to talk about human behavior. As these systems were being adopted, people were responding in interesting ways because they were seeing a system where previously they were either taking taxis or sometimes calling hospital ambulances. And now these other systems were also in play. So how do humans react to this? And interestingly, in the emerging settings is where human behavior is of the most importance. And these influence the first 5 to 10 years of operation of the system. So we really care about how humans are understanding and adopting these systems. So there is a phenomenon that happens that customers, because they now realize they have access to multiple providers, and because they're in an emergency setting, they're of course panicking, perhaps not knowing what to do. They don't have the required medical knowledge. They call the different providers that they want to, or as many as they want. So for example, this patient can call 2 different providers and choose the one which arrives first. It could also call a taxi and depart by that. And so ambulances, we observed, were, even though they were actually trying to serve a call, so we were finding that ambulances were going to serve a call, and then they were finding that the patient was not present at the scene. And of course, the ambulance did not know when the patient lost their willingness to wait and left. They were not willing to wait anymore, either because a taxi arrived, they had a private vehicle, or because the private ambulance arrived, or something else happened, right? And so we wanted to understand what was the patience of the different customers who are using the system. What is the willingness to wait? And can we match that willingness to wait better? So it's not, service is now more nuanced in the emerging settings compared to other settings. It's not just simply sending an ambulance and getting there, but the customer actually being there and us serving them. So we add to this the data inference model. Here we look at past data, and even though we do not actually know when people left, we are able to estimate based on different characteristics of populations. And primarily, it turns out in this case, whether it's an urban or rural area and the kind of emergency that people are calling for, which they would have told the dispatcher on the call, those things influence how long they're willing to wait. And these, using statistical models, we are actually able to estimate these. This is all hidden information, which is called censored information. But if we have good statistical and historical data, we can significantly and accurately estimate how long people are willing to wait. And we estimate the true patience of these different callers. And these models are updated as data is updated in the system. And this can again be embedded within our statistical simulation or queuing based models to optimize for where to locate ambulance. Now we said, well, the current locations of ambulances, the current bases themselves might have locations so that they're not able to serve people well enough. So we said, oh, maybe there are even more important considerations that we need to think about. These are, instead of simply looking at shorter term things like where to locate ambulances, which bases to put how many ambulances at, we said, do we need a larger fleet size to serve this population because many people are leaving the system? Or do we actually need to move the bases around so that they better match people's willingness to wait for the system? And so we undertook that study. The first result was we understood how different sections of the population were able to wait for ambulances. This is called a statistical model for these data, which is called the interval censored data. And using these maximum likelihood estimation models, which are based on a proportional hazards, right? Which means that over time, we estimate that people are less and less likely and willing to wait. But what is the rate at which they might drop out? And what kind of populations are affected? And so we can classify these people into urban and semi-urban or rural, and the kind of emergency they're calling for, whether it's a type 1 or a type 2, or more higher priority or a lower priority. And we also simultaneously say, suppose every street corner of the city were considered a potential base location for ambulances, which is one of the largest models solved in the literature with 13,000 potential base locations. And again, we use that greedy algorithm that I talked to you about. Can we match people's patients to the way the system how we locate ambulances and therefore serve more people? And then we found that compared to the existing base locations, which were in blue here, our system was suggesting, suppose we had the same number of ambulances, where to locate bases. Suppose we could increase the fleet size, where to locate the bases. If we could, this was a double the fleet size. This is what triple the fleet size. If you triple the fleet size, we can match that of what is there in more mature emergency services. But of course, we do not have that ability. Now, what we also show is instead of just tripling the fleet size and not changing the base locations or doing network design, if we do both of these in conjunction, we can do successful service far better. So this green curve is where we actually redesign both the bases and look at various fleet sizes. So with the current fleet size, I can serve, instead of less than 80% of the population, I can serve about 84% of the population. But as I can increase the fleet size to different numbers, now I can say both redesigning the system from a more fundamental level of where to locate, using these street corners as potential locations, but also potentially increasing fleet size over time, can further and further improve service levels in the system by matching how people behave to how the system can serve those people, capturing their behavior correctly. That's the second story. The third story, which I'll speak in, the third and the fourth stories, which I'll speak in much shorter time, so we can have time for questions, is about this notion of decentralized services. So here, this is a unique setting for these emerging economies, including India. And here we use a notion of game theory to model how these service providers themselves are reacting to the fact that people are calling multiple providers. And I'll skip over the mathematics here. But we find that if we think about, if we compare competitive behavior versus centralized behavior, we find that there's an interesting phenomenon. If customers call multiple services, that, of course, the providers or the different emergency services are going to realize, oh, customers are being strategic here. They also take their own strategic decisions of who we provide service to, what is our coverage or catchment region. And based on that, in fact, that decision, again, in reverse, influences the customers. In fact, customers are the ones worst hurt by the strategic behavior. So their strategic behavior, which is myopic, influences how providers behave, and in turn, further affects and deteriorates further the service level that customers achieve. It also reduces equity in society. We can also talk about what kind of bargaining mechanisms or centralization mechanisms government can incentivize, and what are the costs of doing so? What are the incentives government can provide so that either these different services can bargain with each other, provide better service levels to society, or can you centralize the system, and what would be the impact of that? So I'll just skip over the details of that, and I'm happy to answer any questions. Here is a futuristic idea that is, well, not so futuristic. This is being tried in countries like Canada and Sweden. The idea, and it's also being tried a little bit in India. There are apps which allow people who are CPR trained and others to come and quickly perform CPR to, let's say, a particular person whose family may not know how to immediately address that. So if there are trained personnel across a city, whether nurses or others, or even other people with other kinds of or even people with other kinds of emergencies, if people know how to address them, you can have a bystander, somebody who's nearby, come and address this. So an addition to that is to have a drone, a medical drone, fly through the air from its base. Maybe it's closer located than the ambulances, and they're spread out across the city. And these medical drones can come and give you a defibrillator, which can be applied to the patient. And it's very safe. It does not actually affect patients who are healthy, only those whose heart has fibrillated or stopped. So this affects the highest percentage or the most acute of emergencies, which requires the highest or quickest service levels. So there are apps such as Emergency and G1 in India, Pulse Point in Canada, and so on that actually try to serve these with or without the drones. And so we were trying to capture, if we looked at a stylized model of a synthetic city, if I want to serve all these high priority emergencies within a threshold of 8 minutes, let's say 90% of the time, then what can we do? If we did not have drones, in this case, we could say that the maximum service level we could achieve was 75%. If I just increase the ambulance fleet size, we could achieve 85%. It turned out that still some regions, based on how the basis was structured, could remain uncovered. But when you think about the medical drones, they can be spread out more over the city than ambulance bases, which require the infrastructure to be set up for them. So if you could spread out medical drones more over a city, we can find that, for example, these yellow points are where drones could be located and how many are located at each point. We see that the overlay of the yellow heat map on the red heat map shows how much better you can serve. But of course, we're also capturing how people respond. So if we have these bystanders responding at different speeds in urban or semi-urban or rural areas, how can we improve service levels? Does having medical drones help at all if people are not involved? And so on. So we can answer these questions which are related to the upcoming frontier of emergency services and what we can do to actually address and answer these upcoming questions. So again, math is involved in understanding the data, trying to solve for the kind of how to model and capture that data correctly, how to solve for the right decisions we want to make, and what is those impact, or what kinds of decisions, what kind of solutions will have the most impact? Where should a public provider put their money? How can I serve more people well with the least expense, and so on? So I'll stop there and take any questions.
Thank you so much, Professor, for that fascinating peek into how we can actually allocate resources using mathematical models. It's a rather new field for what I suspect most of our audience is. And thank you so much for telling us more about it. We've had quite a lot of questions coming in. The primary one being, what are the main challenges in applying such a math module in a country that's as densely populated and dynamic as India?
That's a wonderful question. And that is where data helped us. And this is, I want to draw attention to how the understanding of the underlying system, the fact that the systems that we were working with, the operators that we were working with actually collected data historically across the system, helped us tremendously. We could not have been running blind, so to speak, if we did not know the kind of patterns that were evolving. And I also want to emphasize that we used historical data, but it's also important that as data is being collected by the system in real time, it's important to incorporate that data and learn from it as we go ahead. Like the aspect of human behavior that I mentioned, for example, that's been evolving over time. The same city, if we look at 10 years before versus when we look at now, humans change. They understand more about the system and therefore they adapt. And in turn, the operator and others also have to continuously adapt. And that's where, again, using the math and using it in the right way becomes very important. So learning from it is extremely crucial.
I see. Thank you so much. I believe we don't have time for more questions, but thank you so much for a fascinating talk. And our audience members can find links to your work in the chat. And I invite them to please absolutely check out more of Professor Lavanya's work if they're so inclined.
Thank you, Misha and Shruti, for having me. Thank you, India Science Festival. It was very exciting being here, and anybody can contact me if they have questions. Thank you.
Thank you so much, Professor, for your time.
Bye.
For our next session, we have a fascinating interview with Professor Anita Sengupta. She's been a veteran of the space program. Her doctoral research focused on developing the ion engines that powered the Dawn spacecraft to the main asteroid belt. She's been a key part of the designing the entry descent landing systems for the Curiosity rover atop Mars. And she also led the development of the cold atom lab that currently lives atop the International Space Station. Post this, she continued to get senior positions and become senior vice president of systems engineering at Virgin Hyperloop. Today, she dons multiple hats, not only as a research associate professor at the University of Southern California, but also as a professional public speaker and a STEM outreach advocate, all the while successfully running her company, Aerospace Experience Technologies. It's a true pleasure having you with us, Professor, and thank you so much for taking our time to speak with us today.
Oh, good evening. Nice to meet you as well. Happy to be here.
So I'm going to ask you some questions, and we have audience members that are tuning in not only in the webinar, but also through a lot of different other platforms in social media. So I'll be moderating questions from all of these sources and looking forward to getting your insights.
Sounds
As we just learned, your experience and credentials are not only storied and impressive, they're also very diverse. Could you tell us a little bit more about your career trajectory and what inspired you to make all of these changes at different points?
Sure. So my background is all aerospace engineering, and my father actually was a mechanical engineer, PhD mechanical engineer. So I always had him as an example in terms of what an engineer could do, and specifically how an engineer can solve problems. So I found that very centering and inspirational. I have always loved space exploration, whether that's from the space shuttle when I was a little kid to science fiction, which I still love to the present day. So I knew as a career choice, I wanted to be involved in the space program. And the best way to do that, obviously, is to become a scientist or an engineer. And I chose the aerospace engineering path. And throughout my career, I was given, or I found new unique opportunities, and I decided to take them. And that's the reason why I moved around quite a bit in terms of what I focused on and specialized in throughout my career in the space program. But after working for NASA, for almost 20 years, I decided it was time for me to go out on my own from the entrepreneurial side of things. And now I have, I founded my own electric aviation company. And I also wanted to do more to help students and young people directly. So I can do that as a professor, both by teaching as well as by having research projects that engage students.
And your focus has focused not only on just space exploration, but also on more terrestrial applications. For example, with the Virgin Hyperloop and what you are doing right now with ASX. What was the motivation for making that switch from the outer cosmos to perhaps a more terrestrial?
So in general, I wanted to solve challenges that were a little bit closer to home, because space exploration is it's exciting and it's fascinating, but it doesn't necessarily solve any of the challenges that we have here at home. So when I was given the opportunity to have a leadership role, an executive role at a green transportation technology company, I felt like that was a really wonderful opportunity to expand my abilities as an engineer in the area of green transportation and actually my abilities as a space engineer to improve on the design of something which was very complicated, but for terrestrial uses. I also like the idea of, as you progress through your career, taking on more leadership roles, specifically as women, and specifically of people, at least in the United States, that belongs to an underrepresented group. So for me, one of the ways to do that was to enter the private sector and also to become an entrepreneur. So, both to further solving challenges that we have here at home, whether that's in India or in the United States, we all have the challenge of climate change. That's pretty much why.
That's actually a very fascinating insight into a very long career. Thank you so much for sharing that with us. And throughout your career, you've led system designs teams for multiple projects. Perhaps one of the most well-known of those is the Curiosity rover and the entry descent landing gear for that. Could you tell us a little bit more about the Curiosity mission and the design process and the challenges you faced during it?
Sure. So the Curiosity rover is part of the Mars Science Laboratory mission, and it was to send a rover to the surface of Mars to conduct a variety of different science experiments focused on understanding whether or not the planet could have once supported life, or even if it's still supporting life to the present day. And the way you do that with a suite of different instruments in terms of understanding the composition of the rocks and the soil, understanding the radiation environment on the surface of Mars, understanding the weather patterns of Mars. But as the engineering team, you could either have been involved in the rover itself, the design of the instruments, or the entry, descent, and landing system that got the rover safely to the ground. It has been done before, sending something to land on the surface of Mars, and it's been done successfully, but this was the largest rover ever sent, and it was being sent to a much more specific location that the science community wanted. So it required the design of a more complex, more precise landing system. And so the discipline associated with that is entry, descent, and landing through a planetary atmosphere. And so there are many different phases to the mission, but the primary job of that phase of the mission is to slow the vehicle down. So the rover is encapsulated in something that kind of looks like a strange looking a bowl, for lack of a better term. And that's done specifically to generate a lot of aerodynamic drag as it descends through the atmosphere. And there are different technologies that are used to slow it down. The first one is a heat shield, which is at the front of the entry vehicle, and that slows it down from supersonic speeds, from 20,000 kilometers per hour down to around 1,000 kilometers per hour. And the next technology is an aerodynamic decelerator, a parachute, which was the portion of the mission that I worked on, which slows it down from about 1,000 miles an hour down to around 250 miles an hour. And then the last portion of the descent is done on retro rockets. I also worked on that portion of the mission, which slows it down to basically a few miles per hour. And so that entire purpose is to sort of target it towards its landing site, keep the rover safe inside of it, but to ultimately slow it down. And all of that has to be done autonomously, which is the reason why it's very complicated, because the distance between Earth and Mars is too far to be able to sort of automatically remotely control a vehicle like that.
Considering the various moving parts and dynamics involved, I think it is amazing how precise the landing happened to the intended site.
And that's where engineering really comes in, because you can't actually test that out ahead of time. So all the terrestrial applications I'm working on now, you can actually build an aircraft and fly it and make sure everything goes as intended, in smaller scales or in remote environments. But for something where you're sending to Mars, you can never actually do that. And the environment on Earth is so different from Mars in terms of the gravity, in terms of the atmospheric properties, that even if you do a test, it's actually not a very valid test, because it changes the performance of all the different systems involved. And it's also a very expensive test. So most of that has to be done through a series of very complex simulations or tests in a subscale environment, which represent a given phase of the entry, descent, and landing. And that's what makes it so complicated. But because now you developed this physics-based understanding for how everything is going to work and how it works together, you're able to predict the performance and do it quite accurately, which is how Curiosity worked this first time around, and it worked really well. As a result, the Perseverance mission coming up is basically a build to print of the Curiosity entry, descent, and landing mission. So now that one has a much higher chance of success because it's been done before.
That's really interesting to know. And that was also one of the largest questions that we have been getting, that in the absence of actual field tests, how are all of these systems designed and controlled?
You can do some field tests. It's just that you can't do it in the exact same environments. You have to pick certain things to check. So in example of the parachute, although you can't test it in the correct speed supersonically, you can test it subsonically in a higher density atmosphere to get the same total load on the structure.
And I'm assuming that the engineers also build in robust safety mechanisms in case things do not go exactly to plan. How are these designed?
So in fact, you can't build in redundancy. So the way that might typically be done for a terrestrial application is that you would have an extra motor or an extra battery. In the case of an entry, descent, and landing system, you can't do that because there isn't enough mass, because the mass has been allocated towards something else and there isn't enough space. So ultimately, the entry, descent, and landing system for Curiosity had a heat shield on it with a maximum diameter of 4.5 meters, which couldn't be exceeded because it wouldn't fit inside the launch vehicle. So you couldn't have added things because it wouldn't have fit and it would have been too much mass, which would have changed the entry performance. So instead what you do is you add in margin to the design and the areas that need it. So sometimes you might add in structural margin. So you expect to see a certain load and then you add 10, 25, 30, 50% margin on top of that, depending upon how well you understand the load that you're going to experience. And then sometimes you might add in margin in terms of having the ability to have more memory or more hard drive space, but there are different ways that you can add in margin. And another important one in the context of entry, descent, and landing is thermal margin. And for a EDL, how much altitude margin you have and timeline margin, which is very, very thin and slim.
Wow, that is almost like an action film, just how many dynamic parts and variables need to be thought of. And it is amazing how our teams of engineers predict things so far into the process. Your next major project actually was the coal atom lab at the International Space Station, which I assume would be a very different design process from the Curiosity rover. Could you tell us a little
Yes.
bit about that?
Sure. So it's very different in that it was an instrument, a science experiment. So now, instead of the goal of working with the teams of scientists, of geologists, ultimately, who wanted to understand the surface of Mars, I worked with a team of atomic physicists who wanted to understand the nature of the atom. So the challenge became a much smaller in size because it was an instrument, the size of, basically a refrigerator, a small refrigerator, but became a lot more precise in terms of the way the system had to be designed because it was a laser optical system which had very precise alignments on the order of microns.
I see. Uh, we can pivot a little bit back to Mars because we have the privilege of having such an expert with us. And a question that seems to come in a lot is, what are your thoughts about the increasing interest in Mars exploration? Not only from government entities, but also private entities all over the world.
I think it's great. I think that when there is interest beyond just the government side, that's kind of the ultimate goal. So the government will invest in something to generate an interest across the board, across different industrial sectors. So then people from those sectors can take over and continue that investment. So I think we've seen that with sort of commercial access to space, with now the fact that we have SpaceX and Boeing and Blue Origin coming up with ways to basically purely as business opportunities to explore space. So I think we're also seeing that with the moon, and we also will see that with Mars. The challenge with going to the moon and going to Mars is that it does cost a lot of money, so it's difficult for a single entity to carry out one of those projects financially, unless the person was ridiculously wealthy, such as but in general, that kind of model isn't a good model because then it's only what he wants, not what's best for a whole variety of people and sectors and things like that. So right now we still see Mars exploration and lunar exploration being a sort of a hybrid effort between the government and other companies. And Mars, because now that we're having an administration change in the United States, will probably become more of a focus, and the moon will probably become less of a focus, which I personally am a fan of because I see us as a spacefaring society. We need to get further away from Earth. We need to do something that we haven't done before. We've already been to the moon. So I think going to Mars is the next best strategy for human space exploration to hopefully set up permanent colonies on the surface.
And is that something you anticipate having in perhaps our lifetimes? A manned mission to Mars?
I do. I definitely think it will happen in our lifetimes. Whether or not it will, whether or not we'll be starting up sort of a colonization process, perhaps not. But I think we will see the first people either orbiting Mars or landing on the surface in our lifetimes. There are many technologies that have to yet be developed because the ones that I spoke about before were developed in the context of robotic missions. They don't have high enough reliability to send people there, and the mass that has to be sent to the surface is much larger for a human mission compared to a robotic mission by an order of magnitude. So there's a lot of work that has to be done over the next few decades to make that happen, but it's absolutely feasible, and it really is only limited by people's imagination and funding.
You also mentioned that we are a spacefaring society, and we want to move more and more further away from our planet. That comes with a lot of increased space exploration. And do you think space exploration, the way we are going about it now, is sustainable? Is this something that we can keep up as a society for a long time? Or do we need to move towards perhaps more greener space technology?
So I don't think it's sustainable, absolutely not. And I think we need to shift our mindset from going back and forth on journeys to low Earth orbit to actually becoming a spacefaring society. So we have people who live permanently in space, or people who live permanently on the surface of Mars, and they're not going back and forth every couple of months, right? So that way you reduce the overall carbon footprint, and then you're basically expanding, right? You're moving out to this new horizon, to this new adventure. Now, the good news is that hydrogen is oftentimes used as a propellant of choice, like hydrogen and oxygen would form. And that is environmentally friendly in terms of the byproduct, of course, being just water, vapor. But hydrogen has to be produced. Is that hydrogen produced using means that are using hydrocarbons? That's obviously not environmentally friendly. Or is it produced in an environmentally friendly way? So we have to actually think about all the way back to the beginning. How is the energy? How are the materials being produced? What is the carbon footprint of that here on Earth? So one other strategy for a spacefaring society is that you don't make everything here on the surface of the Earth. You make it out in space. You make it on the surface of the moon. You make it at mining colonies on asteroids, and then you actually have in-space manufacturing, so you don't have that carbon footprint for these technologies on the surface of the Earth. So we have to have a paradigm shift, which is to truly become an off-world society to reduce the carbon footprint of space exploration.
And is this something that you see playing out in the near future? Maybe like central space.
That's a tough one. So most of it is related to investment, like how much money is it going to take? So it's always completely feasible from an engineering perspective. It's just a matter of getting people together and developing those technologies, but having the money and the time to do it. So I think it's largely an investment by governments as well as the private sector. So the more the private sector can find a business case for space exploration, whatever that happens to be, that will help. But largely it has to be funded by governments working with those private industries, and then a new ecosystem will develop. So I think we're probably several decades away from that. We see it in its early stages, obviously, with communications networks, with weather monitoring and satellites. Hopefully we'll start to see in-space power systems, and those are the beginnings of setting up that in-space infrastructure that we so much benefit from today, right, in the context of communications. So it's really an investment that has to be made with that mindset from governments around the world working together. It can't just be NASA, it can't just be ESA, it can't just be ISRO. They have to work together, pool their resources, pool their expertise, and then it can happen much faster.
It's really comforting to know that there is a little bit more interest in building off-world systems. Particularly, as you said, it has to be a more combined effort. But there do seem to be some sort of questions about the ethics of building off-world systems that are coming up, where people say that we haven't completely ruled out life on Moon or Mars, and should we be taking Earth-based materials to these places? What are your opinions about that?
It's a great question. And what does exist today is a planetary protection treaty. So all of the space agencies around the world agree to certain guidelines that if you are going to send something to a planet that has, or a celestial body that may have life forms on it in some way, you have to make a great effort to ensure that your spacecraft has been cleaned and has had bacteria and bacterial spores removed from it, or at least destroyed by basically heating it up to temperature. So that is something which is already done. So whenever there's a rover that lands on the surface of Mars, or one that might land on the surface of Europa, it has been subject to these planetary protection protocols. Now, when you do a paradigm shift and you actually send people there, we're obviously our own ecosystem with the bacteria and viruses that live within us. So that is a question that has to be answered as a global society. It's not a question just for scientists to answer. It's certainly not a question just for politicians to answer. It's a global conversation that has to be had almost with a venue like the UN to say, do we want to do this? Are we ready to do this? And when we get there, are we going to limit our exposure to only a certain region and do as much as we can to prevent the amount of bacteria that we might transmit to the surfaces on Mars? But it is something that has to be tackled before we get there, well before we get there, in this sort of global conversation as to what the right thing to do is. And I would say that it's really tough, because if you take a hard stance on not wanting to damage another potential ecosystem that might exist, then obviously it's a terrible thing to go bring people there and to bring their own microbiomes there. But I think the likelihood of that being present on the surface of Mars, for example, is very, very low because we've interrogated the surface with a variety of different missions. So if there are microorganisms living on Mars, they most likely live in the subsurface. But I would probably be in the camp that says it's okay as long as we've worked out what the protocols are ahead of time and we do our best to minimize that environmental impact. That being said, though, we have so much more that we need to do here at home to address our environmental impact first. So once we get that figured out, then I think we can start tackling this problem. So I wouldn't want this to be a distraction from the primary problem, which is to reduce our carbon footprint here at home.
These questions seem to come up a lot when we try to, like, a certain camp of people do try to think of Mars as a do-over planet, where once we're done destroying our ecosystems on Earth, we can just sort of transport everybody to Mars and begin again. Now that seems very science fiction-y, but do you think it's as science fiction as it appears to be, or could there be any sense of reality for it?
Well, I think it would be for a very small percentage of beings. So I think we'll never get up to the 8, 9, 10 billion where we're headed and transport them elsewhere. So if that did happen, it would have been catastrophic here on Earth. The majority of Earthlings would have perished, sadly. Only very few would go on. So I don't think that that's even a future worth thinking about, because we know that climate change is solvable, and we need to do that now here at home and not think these alternative science fiction scenarios as a solution, because they're not. They're aspirational goal for us as a people once we've solved our problems here at home and stopped fighting with each other, for example, to go off and things and explore our solar system and explore our universe. But we have to be sound in our judgment and in the way that we conduct ourselves here on our home planet, because there is nowhere else in the solar system, there is nowhere else that we know about in the close by portion of the Milky Way galaxy that will be a home like Earth is to us.
That sounds fair, and perhaps should throw caution to the people who try to think of it this way. Since you are an expert in landing and entry descent into Mars, our audience members want to ask that what could be the potential challenges on doing the same for planets like Jupiter or Neptune, perhaps further out in the solar system?
So there are two different ways that you do entry, descent, and landing. One where you have a planetary atmosphere, a thick planetary atmosphere, like Mars is relatively good. Obviously Earth, Venus is very, very thick, but there are many planetary bodies that don't have an atmosphere. So they use a different approach. So the approach that was used for landing on the moon is more similar to the approach that would be used for landing on the surface of Europa, for example. And in the context of Jupiter, where there isn't really a surface to land on, you would really just sort of like be passing through with an probe like Galileo did, but extremely complicated entry conditions because of the velocity that you're coming with. In terms of the Jovian system or the Jupiter system, it has its own unique challenge of an extreme radiation environment because of high energy particles that are trapped in the magnetic field that Jupiter generates. So that right now is completely toxic to human beings. So that would have to be solved with some kind of radiation shielding technology. For going further out, let's say to Saturn and beyond, the radiation environment is a lot worse than it is at Mars, but it's not as bad as it is at Jupiter. And we have already landed on the surface of Titan, which is one of the moons of the Saturn system. And so once again, that technology exists for robotic spacecraft, but it has to be scaled up to facilitate people landing there. And then when you add in the people mix to it, not only is there radiation, but there's also life support. How are you going to be able to survive on the surface of this world or in orbit around this world for, you know, months or potentially years? You would have to have enough supplies to be able to survive. So there's a lot of challenges involved. So we probably should solve the Mars one first, do that, and then move out. But ultimately beyond Mars, and even including Mars, the big challenge is radiation in the context of human beings.
I see. It's pointing out the challenges for it's not us sitting at home in space exploration. On the same note, there's a fascinating video.
The audio is dropping a little bit.
Okay, can you hear me now? Is this better?
Yes, now I can hear you.
Okay. So there's a fascinating video out there about the 7 minutes of terror when you were trying to land Curiosity on the surface of the planet. And some of our audience members would like to know exactly what was going on through your head and what were you and the team thinking during those minutes.
Well, I think the odd part about it is that there's a time delay. So when you are getting the telemetry data back from the spacecraft or back from the entry system, it's already happened. So for me, I think focused on like, oh, this is so weird because whatever's happened has already happened. It's already landed or crashed on the surface, and we're just seeing the historical record of what I was certainly nervous. I was more nervous about other portions of the mission than the parachute, for example, because I knew so much about it. I spent so many years working on it. So I was more worried, like, you know, once the heat shield was successful, how was the sky crane going to go? Because I felt like that was maybe the higher risk portion, because I wasn't as intimately familiar with the guidance, navigation, control aspect of it. But certainly nervous, but also very excited. And you don't go and work on these types of things because you're afraid that it's not going to work out. You go because you're hoping that it doesn't work out, and it's so exciting, and it's a fun journey to get there.
There are some members of our audience who also want to know a little bit more about the parachute. Like, what was it made of and how did it withstand these extreme conditions during descent?
So parachutes are used for a lot of terrestrial applications as well. You know, people do sport parachuting. They're used for military applications to drop people and cargo. Parachutes are very different in the sense that the atmosphere is so thin that they have to be deployed above the speed of sound supersonically, which means that they have to handle a lot more aerodynamic load because of that high speed. So they're made out of modern materials. The canopy, sort of the soft goods is what it's called, is typically made out of either nylon or polyester, a very strong but lightweight grade. And then there's a structural grid that this canopy material is sewed into, which is made out of Kevlar, which is Kevlar webbing, basically, which is the same material that bulletproof vests are made of. So again, very, very strong, but very lightweight. And it has to be designed in a way so that the load is distributed, even though the environment that you experience on Mars and the supersonic environment, load is not distributed evenly inside the canopy. Sometimes it's distributed unevenly, which means you then have to apply a margin in specific places to be able to get you to a structural network which will survive very harsh loading conditions.
And all of these are tested and designed on Earth in the smaller sub-simulations that you were talking about, right?
So it depends. So we were able to test the parachute at full scale inside a very large wind tunnel, but in a sonic environment to give you the same total load for a sort of uniform pressure distribution. But I also conducted a test program where I made small parachutes and then tested them in a relevant environment inside of a small wind tunnel, which simulated Mars conditions, but a much smaller scale. And then we also conducted a series of computational fluid dynamic simulations and fluid structure interactions to understand kind of what the loading was throughout the canopy to ensure that we had enough margin and that we would get sufficient performance. So you do sort of a combination of both, but our simulations were so sophisticated that we had to run them on supercomputer networks, and they would take weeks just to generate a few data points.
That's interesting to know. Another question that's coming up talks about perhaps the team's attachment to their rovers. This is in context of the fact that there was like a global outpouring of love and sorrow when the Opportunity rover said goodbye in 2019. And the audience members just want to know if that's something that you feel towards Curiosity, or what's the general atmosphere and connections to the missions that you work like at.
Well, I suppose I probably don't feel an emotional connection to the rover just because it is a mechanical device, and you know, I have, you know, pets and things like that, so I have more of an emotional connection to living life forms. But I think that I have so much respect for the amount of energy and expertise and dedication and devotion that went into the success of these missions, even when they're not successful, that I feel for the people behind them who feel sad when the work that they, you know, spent so many years of their life on either didn't work out or has now come to an end. So I feel my empathy is towards the people behind the rover as compared to the rover itself. Now, I didn't work on the prior missions. I only worked on Curiosity, so I don't have that connection to the prior rover. So maybe my tune will change. when curiosity goes. But to this point, I have always focused on sort of like the human beings and the idea behind the mission. But in general, it's almost never bittersweet because you generate so much amazing scientific data, and then you get to use that for the next mission, like Perseverance, for example, so it lives on in its reincarnation.
It was really fascinating also to see how the global community of space enthusiasts perhaps get attached to the mechanical rover itself. And I think it's very indicative of the global interest in Mars exploration, from amateurs to scientists to obviously engineers like yourself who work at the, in the actual constructions of it. Some of our audience members also want to know how exactly do the different teams communicate and interact with each other?
It is very difficult to manage any team, and it's very, very difficult to manage a highly multidisciplinary team. And so there is a field of engineering called systems engineering, which is the key to NASA's success in both human exploration as well as robotic exploration. And without systems engineering, you would never be able to pull off a mission as complicated as Curiosity. And so most other fields within engineering or within software development do not use system engineering. I don't know how they survive, because I'm a system engineering expert, but what it is, the system engineer program starts from the very beginning of the mission. They get the requirements from the customer, whether that's like, science customer or your government customer who's giving you money, to figure out what is it that you want this mission to do. And then they decompose those requirements into lower level requirements until eventually they get all the way down to requirements at the component level. And then you make sure that you have a design which meets those requirements and that you have a way to verify that you meet those requirements, all the way at the lowest component level, all the way up at the system level. And because you go through that process of breaking the problem down and making sure that it works at every stage, all of a sudden now you also have a way to communicate, because now you have system engineers who are constantly monitoring those interfaces at a lower level, at a higher level, who are verifying independently that people have a design that meets the requirements, that their test program actually goes off and generates the data that shows that they will work at that level or at the higher. And it works incredibly well. Most other disciplines of engineering, specifically the automotive sector, and in some ways, even the aviation sector, don't have that. And that's the reason why NASA is able to do what it does so successfully for these really complicated missions, but you have other things simple as a car that don't work that time around.
Thank you for giving us that nice peek in actually what happens behind the scenes. And because these are such complicated projects, I assume that the maintenance for them would also be as complicated, right? For example, the cold atom lab atop the ISS was repaired once by Jessica Meyer and Christina Koch. How do you build in the redundancies and repair mechanisms for these in your systems design and engineering processes?
So for Cold Atom Laboratory was a little bit different because we knew ahead of time that we would have the ability to have upgrades and repairs. So it was designed with that in mind from the very beginning. So part of our system engineering process for Cold Atom Laboratory was to say, we're going to achieve a mission lifetime by having the ability to have on-orbit replaceable units. So we made a decision ahead of time. It's going to be replaceable. And how would the astronauts go about opening up the instrument, taking out the broken item and putting in a new item, and how to make sure that those interfaces work both physically as well as thermally, as well from a software perspective. So we designed it with that in mind.
I see. Okay. And could you tell us just a little bit more about what the Cold Atom Lab actually does for members of our audience who may perhaps be new to it?
It is a facility which uses a technique called laser cooling to cool atoms down to a temperature where they condense and form something called a Bose-Einstein condensate. So we're using only atoms which are bosons, and we're cooling them down to temperatures basically just above absolute zero. And when bosons get down to that temperature and condense, they take on different behaviors, which are very unique. And by doing this experiment in orbit in a microgravity environment, instead of looking at it for a few milliseconds that you do laboratory here on Earth, you can now look at them evolve over a period of many seconds. So we're getting more understanding into the nature of the atom.
I see. Thank you so much for telling us about some of your work during the space exploration program. And now we can move ahead and look a little bit towards your terrestrial work. you're now a research associate professor at the University of Southern California, right? And you've also advocated a lot for working with students and upcoming aeronautics engineers. How, what prompted you to make that change from, some place like NASA and JPL to perhaps a more university space?
Well, I am a researcher, I am a technologist, and I think sometimes the way that you can do the most on the research front is to do it in an academic setting or in a small business setting. When you're part of a really large organization, sometimes it's a little bit harder. And if you want to turn something into a product, which is accessible to the general public, then you can't really do that in a government organization. You have to do that either in academia or in business. And you have the ability to propose to get funding as a professor or as an independent smaller company. It's much harder to do when you're part of a big organization because you've got thousands of other people and lots of different processes to follow. And the organization may not think that what you're doing is worth the organization spending time on. So it's more about being in the driver's seat of your own unique project as opposed to being part of a very, very big team. So I have loved in my career being part of these enormous teams and leading enormous teams, but now, like in the second phase of my career, being able to innovate as a researcher and as a technologist, both in the private sector space as well as in the academic space. And now I can reach out and work very, very closely with undergraduate students and graduate students.
These innovations that you're talking about also seems to be the goal for the current company that you head, right? Aerospace Experience Technology. Can you tell us a little bit more about what your aims are as a part of that company?
So I co-founded ASX about 2 years ago. I came in as sort of like a mid-stage co-founder, and that electric vertical takeoff and landing aircraft system. And the reason why I was involved in joining that effort was because I'm a very active pilot and I know that my flying has a large carbon footprint. So I wanted to develop technologies that would facilitate reducing the carbon footprint of aviation. And so the eVTOL space has that as a goal to be emission-free, lower noise. But during the course of development, I realized that batteries, which was the technology that everybody is focused on in the space, from the big companies like Boeing to the much smaller companies, are not a good fit for aviation because they're too heavy and they don't have good enough energy density. So several months ago, I actually founded a new company, which is called Hydroplane. And so I realized that the right solution to reducing the carbon footprint of aviation is to shift over to hydrogen fuel cells. So now my focus of my entrepreneurial venture is to develop a hydrogen fuel cell power plant for small aircraft.
I see. And a lot of your work has been in the aviation industry, in the space industry, which are traditionally largely considered male-dominated industries. As perhaps not a part of the dominant society, how has that informed your experience over the course of your career?
So, I mean, this is a true sentiment that many of my other women colleagues feel. But when you are part of an underrepresented group, whether it's because you're a woman or you're a person of color like me in the United States, you are held to a much more difficult standard. Oftentimes, you're not maybe treated as well as you should be. You may not be listened to. People might speak over you. They have like the mansplaining and the heap-eating happens all the time. So the only way around that is to become so good at what you do, to become such an expert that people have to listen to you and people have to go to your advice. And so that has been my solution, is to get as much as I can, to get as much experience as I can, so I can be, a lot better perhaps than my male peers. And as a result, I can be in the driver's seat.
That is definitely advice that I hope I will take forward in my own career. And
by the way, it's not fair, but at the same time, there are always going to be things in life that aren't fair yet. But when we are successful as women in this field, we help all the women that come next so that their journey won't be as difficult.
Yes, fingers crossed that happens. You've also done a lot of science outreach work as a professional public speaker, and you have some fantastic keynote addresses out there. What prompted you to sort of go down this path?
So I've always had this strategy in my life where if you don't feel comfortable doing something, you really got to go do that thing. So comfortable comfortable was with public speaking. And so I started off by speaking to little kids. I participated in this after school program that NASA ran, where you could come in as an expert and talk to like 4th, 5th, and 6th year graders. So they're probably like, 9, 10, 11, 12. So teaching rocket science to little kids is very difficult to do. So I figured if I can do that from the communication perspective. So I started off with little kids. And then I expanded to adults, and I joined the Speakers Bureau. And so I got a lot out of it because I got to share stuff that I loved. I got to learn how to be a public speaker. I got to learn how to communicate really difficult subject matter to lay people or to little kids. And it kind of took off from there.
I see. I think that's some of your speeches and some of your public speaking keynotes out there have actually been very inspirational for people wanting to get into aeronautics and aviation. And I was wondering, do you have any message for our young listeners and our young college undergraduate students about how they can pursue a career in astronautics, aerospace, aviation, or even space entrepreneurship?
So I would start off on one level higher, which is whatever you do in your career, it should be something that you want to do, something that you feel passionate about it. If you don't feel passionate about it, you're probably not going to stick around for very long. So don't do something because your friends are doing it, because your parents tell you to do it. You have to do it because you want to do it. And if you don't know what that is yet, then look around, try different things, and hopefully you'll figure it out. And you can do that by volunteering and things like that. Now, in the context of the space program, if you want to be a part of the space program, if you love space exploration, if you do a really good job in school, you will be almost guaranteed to get a good job in the aerospace sector. So there you want to become, aerospace engineer, mechanical engineer, electrical engineer. Some cases, usually not civil, but there are some ground-based applications where you could make use of that. But I would say mechanical, aerospace, electrical are the right disciplines to get into if you want to be on the engineering side. If you want to be on the science side, then you could be an astrobiologist, you could be a geologist. Those are probably the two primary science fields, or astrophysics and astronomer and things like that. So those are the you can focus your academic career to get you to where you want to go. Now, getting advanced degrees is important and very helpful. So if you want to develop technology or if you want to be a research scientist, then you should go and get your PhD. If you just want to do engineering development of a system and perhaps not be sort of in the lead technologist role, then you could, I would say, just get a master's degree. You don't have to get a PhD. But in general, becoming more educated is a wonderful thing. And many people who are in high level positions of leadership have PhDs as well. So they end up doing research for a while, but then they shift over to more of a leadership management role, and it really helps them in their career. So, and then also make use of internship opportunities, whether those are at your university, another university, a government agency, or an industry, and try and do those every single summer. And if you can, even take a semester off to do one.
Thank you for very wonderful insider and profound advice for our young listeners. The last 45 minutes have just flown past, and I'm sure we could talk perhaps for hours more. You've had an interestingly fascinating career, and there's a lot for us to learn. But perhaps one last question that I'd like to end this is, what role do you think public engagement platforms like the India Science Festival play in bringing credible science closer to society?
I think it's really important because young people especially, need to understand what it means to have a career in the field. Who are these people? What do they do? How can I be like them? And hearing from them directly is really important. And in the context of space exploration, sometimes people only think, oh, I can be an astronaut, or I want to be an astronaut. An astronaut represents, like, I don't know, maybe 2% of what the space program does. So I don't think that's the right way to focus career, that I can be an astronaut. You should be, how can I be an aerospace engineer, a mechanical engineer, a software developer, an astrobiologist, a geologist. So by showing people these different career paths using platforms like this, now a lot more people will be reached, as opposed to the people who are like, I'm going to become a fighter pilot and an astronaut, right? So that's why it's important to give people a realistic path to success and understand how there's multiple paths to those success. So by educating them, by exposing them to experts like myself and others, is the right way to do it.
Thank you so much for your wonderful words, and thank you so much for taking time out to speak with us. I speak on behalf of the team of the entire festival, as well as our audience members, that this has been a fascinating hour of conversation, and your insights and your expertise will certainly help a lot of our young audience.
Oh, thank you. And feel free to follow me on Twitter as well. So I do a lot of space tweets on Twitter.
You can find her Twitter handle in the chat. It's been just put in the chat by one of our moderators. And thank you so much for taking time out with your extremely busy schedule to speak with us. Do you have
Have a
any
good
parting
evening.
words for our audience?
Yeah, I always like to use this phrase, which is the sky is not the limit, it's only the beginning. So go out there, make an impact.
Thank you. On that beautiful note, I would like to thank all of you for coming to us at our day 10 of the India Science Fest online. We have an exciting panel of discussions, workshops, games, and interviews lined up for Friday, Saturday, and Sunday. And we hope to see you there. If you have any questions, feel free to reach out to us on all of our social media, the details of which can be found in the chat box. And do feel free to go back and look upon all of our past sessions at our YouTube channel. Thank you very much for joining us today.